Okay, this is section 5.1, constructing. Constructing complex numbers. Now, of course, this is a matrix algebra class, so the way this textbook defines complex numbers is they're going to use a 2x2 matrix, and I just want to explore some things with that. So typically, what you're used to is a complex number z is made of a real part plus I times an imaginary part. And so that's, I think, something to understand about vocabulary is if I talk about the real part of z, like that, that's x. If I talk about the imaginary part of z, that's y, which is a real number. So the imaginary part of z is the real number y in this case. The imaginary number, if I had a pure imaginary number, might be something like y times I. But when you talk about an imaginary part, okay, so we're saying the real part of z, and we're saying the imaginary part of z. And so, those are just some things to realize, is that the funny thing is the imaginary part of z is a real number y. But in thinking about it that way, we could also say that we're going to think of z as a 2x2 matrix of the form x minus y, y, and x. And so if you have something like this, then it's kind of interesting, because see, all these are real numbers, but it's a 2x2 matrix. Okay. Now, I think one of the things to do is to show, for one, this is a subspace. 0 is certainly a part of this, right? So the 0 matrix is 0, 0, 0, 0. And, that's definitely of the right form. And then we can check addition. So if I have a z1 plus a z2, that is x1 minus y1, y1, and then x1, and then plus an x2 minus y2, y2, x2. And so that is x1 plus x2 minus y1 plus y2, y1 plus y2, and x1 plus x2. So you see, it works there for addition. And what about multiplication? So if I took a z1 times z2, that's x1 minus y1, y1, x1, and x2 minus y2, y2, x2. And so multiply those together, I get the 2x2 matrix. Well, I'll get a x1, x2, and then a minus y1, y2. And then for the next part, let's see, the row 1 times column 2, I get a negative x1, y2, and a negative, so I'm just going to put a negative around that whole thing, x1, y2, and then plus y1, x2, like that. Bottom row, I get I'll get an x1, y2 plus y1, x2. So you see that's looking like it's the right form. And then finally, for the last part, bottom row, second column, I get a x1, x2 minus y1, y2. Okay, so it's closed under addition, and we can kind of see how this addition works. And, in particular, how the multiplication works. And so notice that, you know, this minus y1, y2 sort of helps with this idea that I, you know, the number I, the imaginary number I, is the square root of -1, because I times I would make -1. Because if we want this to match up, so you could, even if you had not decided that I was the square root of -1, you know, if you match this up, if I simply take an x1 plus I y1 times x2 plus I y2, well, when I multiply those together, right, I get an x1 x2, I'll get plus I squared y1 y2, and then I will get plus an I times my x1 y2 plus x2 y1. So when I multiply this thing out, you know, this is what I get. And so, you know, here is that same imaginary part that we have up there and down here. But then here, the real part, you know, I get an x1 and x2, and then I get plus I squared y1, y2. So that seems to indicate then that I squared would be -1. So this is x1, x2 minus y1, y2 plus I times x1, y2 plus x2, y1. So, you know, multiplication, you know, starts to be kind of a mess, because, you know, it really, you can think of it as, gee, you know, just to multiply these two complex numbers, I have to do a 2x2 matrix multiplication in essence. Okay, but that's kind of neat that you can represent them this way. So we did our addition, we did our multiplication. Now they use, you know, they use their curly braces to, when they first start talking about x and y, the real complex numbers. But you know, I'm not going to bother with that. They reasonably quickly say that, you know, yeah, we just talk about x, we drop the curly braces and talk about x plus iy. Okay. And so, you know, notice you have the identity, right? If you took z times the identity matrix, that would give you z. And so since the identity 2x2 is 1, 0, 0, 1, then you know, our multiplicative identity is 1. Okay, multiplicative identity is the number 1. And so let's see, we can, equating, yeah, so I'm just kind of looking through their stuff. You know, we equate, you know, so right, we equate two matrices by equating their individual elements within the matrices. And so, if well, yeah, so Z1 equals Z2 if X1 equals X2 and Y1 equals Y2. But again, in the matrix form, right, if I had this X1 minus Y1, Y1, X1, and I wanted to say that was equal to X2 minus Y2, Y2, and X2, then, right, I would have to match up components, so I would have to have that X1 equals X2 and Y1 equals Y2. Okay, so, again, that's the part of the matrices. Now, if we want the multiplicative inverse, certainly, the multiplicative inverse of a real number. So if I had, say, a real matrix, x, 0, 0, x, like that, and I wanted its inverse, well, that would just be 1 over x, 0, 0, and 1 over x, like that. Okay, but again, if I have a real number, right, its multiplicative inverse is just the 1 over its reciprocal, 1 over x. And but now, let's think of just the multiplicative inverse of something like this. Right? If I want the multiplicative inverse of that, well, I could use we could use our inverse formula. We could do row reduction, right? So if I want to use my inverse formula, I need 1 over the determinant. So the determinant of this thing would be x squared plus y squared. And then times, and let's see, what the heck is that? I have to think about that a little bit. These would be x and x, and then I can just never remember where the negatives go. I believe the negative would go here, and that's positive. Those are what they switch there. Now, since the diagonal is x, you can't see that we switched a and d, but you can see that we took the negatives of the opposite two corners, the off diagonals. And so, as you look at something like that, it says that the multiplicative inverse, so if I write it as x plus iy, and I say, well, I want the multiplicative inverse of that, we would write that as, I'll write the x squared plus y squared first on the bottom, and then it would be x minus iy. Okay, because we've switched the negatives here, so that would be x minus iy. And let's check that. So mostly I just need to check that the numerator here times x plus iy gives me x squared plus y squared. And so let's take x plus iy times x minus iy over x squared plus y squared. And so we get x squared. We'll get minus I squared y squared. And then the because this is, you know, the difference of squares here, we've got these conjugates, and I'll mention that more here in a minute, but these are conjugates on top with the plus and minus, right? The middle terms disappear, and so we get our x squared plus y squared here. But now I squared is -1, but it's the negative of that, so that is indeed x squared plus y squared over x squared plus y squared, and that equals 1. Okay, so that's our multiplicative inverse. And so I can also use that idea to divide two complex numbers, right? So suppose I have z1 divided by z2. Well, that's the same thing as z1 times z2 to the, oops, -2, you know, z2 inverse. And so that would be my x1 plus y1. And then my multiplicative inverse for z2 would be x2 minus I y2 over x2 squared plus y2 squared. And so this is equal to x1, x2, and then I will get my minus I squared, so I'll do that as a plus, and a y1, y2. So there's the real part, and then plus I times, and I have an x2 y1 and a minus x1 y2, all divided by x2 squared plus y2 squared. So there I've done a division. Now another way you can do that division is that, you know, if I have just written it as x1 plus y1, sorry, iy1, so let me get that fixed. iy1 divided by x2 plus I y2. Well, to fix this, we do multiply by that thing called the conjugate. Okay, and so just over here, if z equals x plus iy, then we denote z conjugate with that line. So it's kind of weird in this vector stuff because that z conjugate looks kind of like I'm saying the z vector, but it's the z conjugate, and that's x minus iy. So you just negate the imaginary stuff there, and so if I take then x2 minus iy2 over x2 minus iy2, you see that then I end up getting what I had there. This is equal to on the top to the x1 x2 plus y1 y2, and then plus I times x2 y1 minus x1 y2, and on the bottom I get that same x2 squared plus y2 squared. Okay, so, you know, I could have left it looking like that, but we usually don't, because that's not the typical form of a complex number, right? We want a complex number to look like this, and so that is our division. So that's my grandson coming in. Okay, and let's see, so I've got the identity, we mentioned that, and I think I hit everything in there. If I didn't, we'll catch it when we get to it. But there we go, that's section 5.1.